Hi, sometimes you just want to sit down, do your job, try to make a good video, have a nice sponsor, and make some nice juicy internet money. But no, your house has to break down. What's the problem, you ask? Well, some areas at home are cold because our heater doesn't heat them anymore. I guess we fixed that now. Well, I don't think this thing is broken. Well, they call it a combi heater, a combinational heater that heats water for showers and such, and also separately heats water for baseboard heaters. And our baseboard heaters are like these type of radiators that hot water runs through them to create the heat. It is a tankless device. It takes a small footprint to do all that work, and I think it's working because it's creating hot water and some areas of the house are getting warm. Now you might say, maybe you're an electrical engineer, not a plumber. Really? Did you say that? For your information, the hierarchy is like this: electrical engineers, astrophysicists and rocket scientists, electrical technicians, then plumbers, and doctors too, because they basically do plumbing work, other labor, and yeah, mechanical engineers. Got 'em! Anyway, the hot water comes out of this pipe and goes to this magic device, I don't know what it is, and then splits into 5 zones in the house and returns from that pipe to the other side of the heater. So basically we have a closed loop the hot water runs through, except if you look here, for some reason the hot water that comes out is short-circuited here that returns right back to the heater. Is that the right way to do it? So it seems with this short circuit here, before the hot water gets to go out, it just returns straight back to the heater. It is the right way to do it. Maybe I promote plumbing to rocket science. Anyway, the 5 zones in my house are controlled by these electric valves that are controlled by the signals coming from the thermostats. My thermostats are these Nest smart thingies that I can also control with an app. Okay, let's think. You know, those thermostats might be doing something, trying to be smart. You know, they sense when I'm away and shut down all the zones to save power. Maybe they are in some power saving mode. I guess I can force it on. Now I'll wait for a few minutes and look at it again with my thermal camera. And nothing, eh? Let me turn on another thermostat. Oh, this guy is getting warm. I guess we can check and see if the thermostats actually send signal to the valves. I just don't know what is what here. So I figured these 2 bottom valves don't open. I should be able to open them somehow. There's a screw on the side of it and I have this sideways screwdriver. Should be able to open it up. There we go. So it seems I can see 2 components in here. This seems to be the motor that turns the valve, and there is, if you can see back there, a switch that probably senses something. These lines go to the motor thingy. I want to see if they get any signal from the thermostat. Just turn the temperature high and measure the voltage. And what do you know? There's nothing. Is this one the same? Let's check a good valve to see what to expect. Just turn them all high. I hear something's happening. Ooh, something switched. And the heater is on. So this guy's running. Let's check the voltages. Nothing. Nothing. Nothing? The hell? Oh, are they AC voltages? Oh, look, 29 volts almost. 29 volts AC and almost 29 volts. Damn, so they all have signals. What is that noise this is making? Let's try and pull these caps off. Seems like an AC motor that doesn't really want to turn. How about this one? Now that you're at it, that one! Let's turn the bottom one off. Hey, it's turning. Middle one, no motion there. Seems like a free spirit. And the top healthy one, oh, there you go. Turned off. Let's turn the healthy one back on, see what's supposed to happen. When I turn it on, it starts rotating like that for 10 seconds. At some point, a lever will push against the switch. The switch signals to the heater that the valve is open. It starts heating up the water and turns this thing on, whatever it is, and the hot water starts flowing. And when I turn it off, a spring pulls the motor back, releases the switch that signals to the heater that the valve is closed, and everything turns off. Now with that bottom motor, see, there is some friction. It doesn't want to turn properly. And the other motor seems to have a disconnected wire and doesn't get any power. Bye-bye, motors. These simpletons worked for less than 2 years and failed. What a disappointment. Okay, let's test these motors, which seem to have been running on 30 volt, 60 hertz AC, I assume. So I have to step down the AC line to what these require. These motors are typically very low current, low power motors that using gears are... We can still cut it open. One must first lower the supply voltage to the required value before connecting the load. And of course, 30 volts is safe to touch. Jeez. And of course, 30 volt would be safe if you didn't have any cuts and bruises on your skin, because it's your dead skin cells that have high resistance blocking the current from going through your body. But if you have any cuts exposing low resistance body tissues, the current will be much higher and will hurt. And I guess if your skin is wet and you push against it, yes, I feel it. So we should say low voltage is safer than high voltage, and depending on your skin condition, you could still get shocked and die. Let's focus on the motor. I think I killed this one. Smells burned. Oh hey, it still turns, and it turns much more smoothly too, although I can feel some vibration in there. These motors are very low speed, low torque motors you can easily stop, that using the gearbox underneath them, they increase the torque. Seems like burning this motor fixed it. I don't know if I can trust it enough to put it back, but I'll keep it just in case. And I think this motor was the one that seemed to have a disconnect inside that didn't turn at all. This is the motor that had the friction but was turned. This is the one that had the disconnect and high voltage burned and fixed it somehow. And they say high voltage is bad. So yeah, this one seems like there is some misalignment or something. Maybe if I push and pull on it. Nope. So I guess we can do a surgery on this one and see what's inside. Let's pry it open. Oh! There we go. That's just the gearbox. Maybe you can just cut it. There we go. Here's what it looks beyond the covers. There's all the windings. I'm still not reaching any windings. These are all just magic of phase shift and such to make the motor turn with a single phase. And it is an induction motor. This is the rotor that is not magnetic, but the changing magnetic fields create currents in the rotor that forces it to turn. Well, let's at least measure the resistance and inductance of the coil to get a... What are you burning? So the coil resistance is around 22 ohms and its inductance is almost 80 millihenry at 100 hertz. This means the coil at 60 hertz has around 30 ohms of inductive impedance, and plus the 22 ohm resistance, we get around 37 ohm total impedance. They are rated for 24 volts, which means there will be 650 milliamp continuously running through them. So there will be 15.5 watts of apparent power running through these motors. In our area, we are not charged for reactive power, but the current is there and wastes energy through the resistance of the transmission lines. Well, on 120 volts, it is more like 150 milliamps. But imagine if all 5 zones are on at the same time, then the current goes up to 0.75 amps. Now you might tell me, Mehdi, you are calculating the current for a motor with no rotor. When the motor turns, the current drops. Well, that would be true for high torque motors. For these ones, First of all, they are so weak and low torque that even at no load, the current is not much different. And also, we saw how they work. It turns a few times until the lever turns and opens the valve and pushes against the switch, at which point it stalls, staying on for the rest of the operation as long as the heater is on. It has to stay on to push against the switch and fight against the spring that is trying to pull it back. When the heater is off, it is de-energized and the spring can pull it back. This is a stupid design if you ask me, wasting a bunch of power on windings and the lines. The motor doesn't need to stay on when it is stuck in a certain position. I'm guessing they did it because they wanted to stay backwards compatible with old inefficient systems. All you need is a DC motor and no springs. Just turn it on until it pushes a switch and then turn off. Then turn it in reverse until it pushes another switch and turn off. Save a ton of power. But I guess I'm stuck with this for now. Let's see if I can buy some replacement motors. This is the original Honeywell motor for $59, 24 volt. DC 60 Hertz. Okay, here's a knockoff version for $37. Let's buy this one. There we go. My two new motors are in and they seem to be perfect replicas. Actually, let's pop a cap and see how perfect is perfect. They are very much the same. Now we just pop the new motors in and hope for the best. They are fitting just fine. AC, there is no polarization. Pop and pop. Strip, strip, twist. And use one of these wire nut thingies, whatever it's called. Then turn and done. Now let's pop the caps and see them in action. Okay, let's turn them on. The first one is on. The second one is on. And the third one, just for reference, is on too. There we have it. Now we just put all the covers back on. Wait, I have to put the caps back on first. All these motors are rated for 24 volt AC, but I measured 29-30 volts across them. Maybe that's why they're dying. I bet the transformer is in the controls here somewhere. Do you want to know how my plumbers do electrical work? Here. This is the power line. First you cut it in half, then you connect it back together before feeding it to the device. Also, you connect the white wire to the black wire and the black wire to the white wire before connecting it to the terminal. And why these two lines didn't go straight to the terminal? No one knows. Anyway, this transformer is the one that converts 120 volts to 24 volts AC that goes out to the rest of the circuit through the white and black lines. Measuring its voltage, I am almost getting 31 volts AC. Let me turn on all the heaters and see how much the voltage drops under maximum load. And with all the valves on and motors running, I have 26 volts. That's what you get with an unregulated power supply. You have to pick its voltage higher than normal so that when all the loads are connected and its voltage drops, the loads can still run properly. But then you risk damaging your motors because you're typically running them at a voltage higher than the rated voltage. Done! And now we hope that these new motors will last much longer than the old ones. It's interesting how this plumbing problem turned out to be electrical. And now we'll go on to make, I guess, similar videos. See ya!